underwater volcanoes erupt. Constantly beneath the calm blue surface of the Atlantic Ocean lies a mountain chain few people ever think about. It stretches more than 16,000 kilometers across the planet, running from the Arctic Ocean to the southern Atlantic. Scientists call it the Mid-Atlantic Ridge, a vast seam where Earth's crust is slowly tearing apart. But this is not a quiet place. It is one of the most volcanically active environments on Earth. Along the ridge, the planet's tectonic plates are drifting away from each other at a rate of a few centimeters per year. That movement may seem slow, but over geological time, it creates enormous tension inside the crust. As the plates separate, molten rock from the mantle rises upward, filling the growing gap. When that magma reaches the seafloor, it erupts, not occasionally, but almost continuously. Most of these eruptions are hidden beneath kilometers of water, far from human observation. Instead of explosive fire and ash like volcanoes on land, underwater eruptions behave differently. The intense pressure of the deep ocean prevents large gas explosions. Instead, the magma oozes out slowly, cooling instantly when it meets the freezing seawater. This process forms strange, rounded structures known as pillow lava, bulbous mounds of basalt that stack upon each other like enormous piles of black cushions. Entire sections of the ocean floor are built from these formations, layer upon layer, recording thousands of past eruptions. In fact, scientists now believe that most of Earth's volcanic activity happens underwater, not on land. According to researchers at the U.S. National Oceanic and Atmospheric Administration, NOAA, more than 75% of the planet's magma output occurs along mid-ocean ridges, where submarine volcanoes are constantly creating new crust. Every time magma cools and solidifies here, the ocean floor grows slightly wider. The Atlantic Ocean itself is slowly expanding. Direct observations of these eruptions are rare, but when remotely operated vehicles capture them, the scenes are extraordinary. Jets of molten rock spill across the seabed, while shimmering clouds of superheated water surge upward into the dark ocean. Temperatures inside the lava can exceed 1,100 degrees Celsius, yet just a few centimeters away, the surrounding water is near freezing. It is a violent meeting of fire and ice. Yet despite this constant volcanic construction, eruptions along the ridge rarely produce the dramatic disasters associated with volcanoes on land. However, because these volcanoes sit directly along tectonic plate boundaries, activity in one region can sometimes influence stresses across the same plate system. In some cases, volcanic activity, earthquakes, and tectonic fractures may occur within the same network of forces shaping the ocean floor. The immense weight of the ocean suppresses explosive eruptions, turning most of them into slow but relentless outpourings of magma. Over millions of years, this process has shaped the very structure of the planet. Nearly every ocean basin on Earth is slowly spreading apart along similar ridges hidden beneath the waves. The seafloor is not a static landscape. It is being rebuilt continuously, silently, and almost entirely out of sight, and the Mid-Atlantic Ridge is one of the places where that process never stops. Black smokers create ecosystems without sunlight. Far below the sunlit surface of the ocean, there are places where life should not exist at all. At depths of 2 to 4 kilometers, sunlight has long disappeared. Temperatures hover just above freezing, pressure is crushing, and food from the surface arrives only as a slow drift of particles known as marine snow. For decades, scientists believed the deep ocean floor was little more than a barren desert. But scattered along the mid-ocean ridge, explorers discovered something completely unexpected: columns of black smoke rising from the seafloor. These towering structures are known as hydrothermal vents, and the most dramatic among them are called black smokers. They form where seawater seeps deep into cracks in the ocean crust. As the water travels downward, it is heated by magma lying beneath the seafloor. Temperatures can exceed 350 degrees Celsius, hot enough to dissolve metals and minerals from the surrounding rock. Then the superheated water surges back upward. When it bursts out of the seafloor and meets the freezing ocean, the dissolved minerals rapidly solidify, creating towering chimney-like structures. Iron sulfides in the water give the plume its dark color, producing the billowing clouds that resemble smoke. But these vents are far more than geological curiosities. They are the foundation of entire ecosystems. In most environments on Earth, life ultimately depends on sunlight. Plants and algae capture solar energy through photosynthesis, forming the base of the food chain. Here, however, there is no sunlight at all. Instead, life relies on chemistry. Microbes living around hydrothermal vents use a process known as chemosynthesis. Rather than using light, they extract energy from chemicals such as hydrogen sulfide pouring out of the vents. These microbes convert chemical energy into organic matter, effectively replacing the role of plants in this dark environment. And where there is food, life follows. Around black smokers, dense communities flourish in the darkness. Giant tube worms, over 2 meters long, cluster around the chimneys, their red plumes waving in the mineral-rich water. Swarms of shrimp, crabs, and strange vent fish patrol the rocky terrain. Clams and mussels anchor themselves near the vents, relying on symbiotic bacteria inside their tissues. Many of these animals have never been found anywhere else on Earth. What makes these ecosystems even more astonishing is how isolated they are. Hydrothermal vents can be separated by hundreds of kilometers of empty seafloor, yet each one hosts its own thriving biological community. The discovery of these vents in 1977 during a deep-sea expedition near the Galapagos Rift completely changed scientists' understanding of where life can exist. Until then, it was widely assumed that sunlight was essential for sustaining ecosystems. Black smokers proved otherwise. They revealed that life can flourish using energy drawn directly from the Earth itself. Today, these deep-sea oases continue to reshape our understanding of biology. Some scientists believe similar chemical ecosystems might exist beneath the icy crusts of distant moons, like Europa or Enceladus, where sunlight never reaches hidden oceans. In the darkness of the deep sea, the rules of life are rewritten. Here, the food chain does not begin with the sun. It begins with the heat of the planet. Massive tectonic fractures span the planet. To someone standing on the shoreline, the ocean appears calm and endless. Waves rise and fall, tides come and go, and beneath the surface, it feels as though the seafloor must be as solid and permanent as the continents themselves. But that impression is completely wrong. The ocean floor is split by enormous fractures that span the entire planet. These fractures mark the boundaries of Earth's tectonic plates, massive slabs of crust that slowly drift across the surface of the planet. There are more than a dozen major plates, along with dozens of smaller ones, all moving at speeds roughly comparable to the growth of a human fingernail. Where these plates meet, the crust breaks. Nowhere is this more visible than along the Mid-Atlantic Ridge, one of the longest geological structures on Earth. Stretching from Iceland in the north all the way to the Southern Ocean near Antarctica, the ridge forms a colossal crack running down the center of the Atlantic Basin. Yet the ridge itself is not a single continuous line. Instead, it is segmented by countless tectonic fractures, known as transform faults. These faults slice across the ridge like giant scars, offsetting the seafloor by tens or even hundreds of kilometers. From above, the pattern resembles a long zipper stretching across the ocean floor. Each segment of the ridge is slowly pulling apart. As the plates diverge, magma rises from the mantle to fill the gap, forming new oceanic crust. But the motion is rarely smooth. The Earth's crust does not slide like a well-oiled machine. It sticks, strains, and then suddenly shifts. When that shift happens, enormous blocks of seafloor can move abruptly along these fractures. These movements reshape the seafloor continuously. Over millions of years, tectonic fractures have created some of the largest geological features on the planet. Deep valleys, called rift valleys, cut along the centers of many mid-ocean ridges, marking the place where the crust is actively being torn apart. Nearby fracture zones stretch outward for thousands of kilometers, leaving permanent scars in the ocean floor that can be detected even from satellite measurements of sea surface height. Together, these structures form a vast network of cracks that circles the entire globe. The Mid-Atlantic Ridge is only one piece of this system. Similar ridges run through every ocean basin, linking together into what geologists call the global mid-ocean ridge system, a continuous chain of underwater mountains and fractures stretching more than 65,000 kilometers, making it the longest mountain range on Earth. And it is still growing. Every year, new crust forms along these fractures, while older seafloor slowly drifts away. The Atlantic Ocean widens by several centimeters annually as the continents on either side move farther apart. What appears from the surface to be a stable seafloor is, in reality, a constantly shifting mosaic of plates, cracks, and fractures. The ocean floor is not a fixed landscape. It is a planet-sized system of moving seams, quietly pulling the Earth apart. Earthquakes below the ocean trigger tsunamis. Far beneath the ocean surface, the planet is rarely still. Along the boundaries where tectonic plates meet, immense forces build silently over decades, sometimes centuries. The plates push, grind, and lock together, storing enormous amounts of stress deep within the Earth's crust. Eventually, that stress becomes too great. When it finally releases, the result is an underwater earthquake. Unlike earthquakes on land, many of these events occur along subduction zones, places where one tectonic plate is forced beneath another and sinks slowly into the mantle. These zones are among the most powerful geological environments on Earth, capable of producing earthquakes with magnitudes greater than 9. But the shaking itself is only part of the danger. When a large earthquake suddenly shifts the seafloor upward or downward, it displaces an enormous volume of water above it. The ocean surface responds instantly. A massive pulse of energy spreads outward in every direction. This is the beginning of a tsunami. In the open ocean, tsunami waves are often almost invisible. They may rise only a meter or less above the surrounding water, passing beneath ships without being noticed. But what they lack in height, they make up for in scale. Some tsunami waves can stretch hundreds of kilometers across and travel at speeds exceeding 800 kilometers per hour, nearly as fast as a commercial jet. As these waves approach shallow coastal waters, something dramatic happens. The slowing ocean floor compresses the energy of the moving wave. Water that once spread across a vast area begins to pile upward. The wave grows taller and steeper, transforming from a subtle swell in the open ocean into a towering wall of water. By the time it reaches the coast, it can devastate entire regions. One of the most powerful examples occurred in December 2004, when a magnitude 9.1 earthquake struck off the coast of Sumatra along a subduction boundary. The sudden movement of the seafloor triggered a tsunami that swept across the Indian Ocean, affecting coastlines in more than a dozen countries and causing one of the deadliest natural disasters in recorded history. Events like this reveal how tightly the ocean and the planet's internal forces are connected. The seafloor may appear silent and distant from human life, hidden beneath kilometers of water. Yet the tectonic fractures that cut across the ocean basins are constantly shifting. Most of the time, the movement is slow, but when the Earth suddenly releases its stored energy, the consequences can travel across entire oceans. In a matter of hours, a fracture thousands of meters below the surface can send waves racing across the planet, reminding us that even the deepest parts of the ocean remain deeply connected to the world above. The deep ocean still holds more mysteries than answers. Subscribe to explore what we have yet to discover.